get started with the next session. So the next session, we have one qubit. We have Daniel Crawford from 1QBit. We also have Landon Downs here from 1QBit. And Landon passed through Bristol probably a couple of months ago and gave a really inspiring talk to our sort of younger members of the group. So we have a Center for Doctoral Training in Quantum Engineering. And Landon Downs, who's one of the founders of QBit, came in and effectively gave his story to the students about how they formed this company, and was really trying to inspire our students to think of future careers that aren't in academia, and trying to inspire them to maybe think about starting their own company. And Landon mentioned about the company and about their this API that they were putting together, and we figured it would be a good opportunity for them to come and show the community what they're doing. So without further ado, I'll introduce Daniel, who will tell us a little bit more about 1QBit and about the sort of things that they're doing.
Cool.
Thank you, Daniel.
Is this thing on? Yeah. Okay. Hi, everyone. Thanks for having me. This is going to be more of a high-level talk than the last two presenters, which is either a good thing or a bad thing, depending on how tired you are by now. 1QBit is a software development company that's focusing on abstraction away from quantum hardware. So we have a team of about 46 researchers that are working to develop a platform that allows people that aren't necessarily experts in quantum computing to access quantum hardware. Since we're based in Vancouver, we are working very closely with D-Wave, since they're our neighbor company. So a lot of this talk will be based around our software development kit for adiabatic quantum computing. So the talk will include some motivation behind why we developed the software development kit. It will go into a couple demos showing how different users might access the SDK and use it for optimization problems. And with that, I'll go into it. So the goals of the company, we really want to create a community around quantum computing. So right now, quantum computing is not necessarily a very accessible field by people that want to experiment with technology. So we want to provide users with an opportunity to interact with different types of quantum architecture. So right now, we are allowing people to operate adiabatic quantum computers more easily, but we are definitely interested in including other types of technology as you guys create it. We can provide the software to abstract away from the hardware and allow people to access your technology. So the rest of the talk will be based around our software development kit for the D-Wave quantum annealer. And I'm sure you're all familiar with this technology. So why do we want to build a quantum annealing SDK? We want to broaden access to quantum annealing computing. We want to let people who are not necessarily mathematicians or physicists access adiabatic quantum computing methods. We want to abstract away from the quantum hardware so people don't have to worry about words like quantum or binary optimization or quadratic polynomials, anything like that. So we don't want them to have to use the quantum machine code. So just like a typical software developer doesn't actually access the binary operations of a CPU, we have compilers and programming languages. We want to provide the exact same situation for quantum computing. We want to build simulators that run on classical computers that can emulate what the D-Wave architecture is doing, so that even though D-Wave might not be able to solve all of our problems right now, we'll be able to switch back and forth between quantum solutions and classical solutions. Finally, we also want to provide tutorials, code examples, complete method descriptions in our documentation so that it's very easy to jump into programming with our SDK. And we want to enable users to leverage pre-built library of functions, so off-the-shelf components that are typical optimization algorithms that don't necessarily require knowledge of quantum mechanics. So our audience, we have 4 groups that we're targeting for this development. There's data analysts, application developers, students, and optimization experts. The 3 categories, analysts, developers, and students, are people that might be very interested in using optimization problems, but they don't really care about how the solutions are actually generated. So they don't really care that there's a huge computer developed in Burnaby that's producing these minimal solutions, but they definitely want the answers to their problems. The optimization experts are people that know how to reduce their problems into a form that an adiabatic quantum computer might be able to use. So in this case, it will be formulating QUBOs or icing models that are directly embeddable onto the D-Wave architecture. So before I go into the demos, I'll talk about what challenges we've overcome by creating the SDK, and I'll also go into the actual architecture of the SDK. So first of all, the challenges that we feel have been readily addressed by the SDK, the first one is embedding. So as I said, you have to reduce an optimization problem into a form that the quantum computer can understand. So this will be in the form of a QUBO or a quadratic unconstrained binary optimization problem or an icing model. So this is a fully connected graph problem that needs to be embedded onto the D-Wave native architecture, which isn't necessarily fully connected. It's a sparse chain of chimera graphs. So actually embedding this fully connected QUBO onto this graph is computationally expensive. It's an NP hard problem. And you have to do it for every optimization problem or every QUBO you generate. Manual errors. So dealing with adiabatic quantum computing in general is non-trivial, since it's a non-trivial technology. So in this case, non-trivial implementations can lead to many errors, so human errors and coding errors. And without the appropriate debugging tools, creating algorithms can be very, very difficult. Implementation effort. So developing optimization algorithms starts with coming up with an idea, implementing the idea, benchmarking, going back to your original idea, tweaking it a bit, implementing again, benchmarking. So if implementation is difficult and prone to errors, the algorithm development becomes very slow and it's simply inefficient to do this. It's also very discouraging for developers to even want to try to use quantum computing in the first place. Interfacing with hardware. So the main goal of the SDK is to abstract away from the hardware so that you don't actually have to deal with any of the downfalls of the hardware, which could be faulty qubits, the evolution of the technology, or architecture changes from chip to chip. Finally, optimizing to QUBO. This requires expertise not only in optimization, but optimization of quadratic binary or value functions. And as I said before, not every QUBO is suitable for the D-Wave architecture. So it's this knowledge you are required to actually start to use the D-Wave processor that is a hindrance. So it's very time-consuming and recurring for each problem. So to motivate the fact that we've overcome these challenges, I'll just show you these pages of code that have been written by one of our research teams. They're actually building a graph similarity project. This is before they had access to the SDK, so they're actually doing the embedding, doing the QUBO formulation, and spending many months on research and development to make this. After we have access to the SDK, we can do this in 10 lines of code. So it's very, very accessible code now. So I'll talk about the actual architecture of the SDK. It's usable out of the box, it's fully configurable, it's suitable for a wide range of audiences, from the optimization experts to people that don't necessarily have an optimization background. It's built in 3 layers. So we have an algorithms layer, we have a binary polynomial layer, and we have a common solver interface layer. The algorithms layer is going to be aimed towards the analyst, developer, student type person. And these are people that know what type of optimization problems they want to tackle, but they don't necessarily know about the quantum computer that's underlying the process. So things on this layer are classic optimization problems, max K quasi-clique, graph similarity, linear knapsack, which are very common household optimization names. But you'll notice that there's no mention of quantum, there's no mention of quadratic polynomial, there's no optimization here. The second layer, binary polynomial, this is aimed towards the optimization experts. These are people that know how to distill an optimization problem into a QUBO format or an icing model format. So this layer provides operations and data structures that allow them to construct QUBOs from scratch. So they can actually manipulate this layer in a way to create the algorithms that are on the algorithms layer themselves. So it provides the next level of abstraction away from algorithms. Finally, the common solver interface layer. This is sort of the heart of the SDK. We have a D-Wave solver, which is the quantum solver, as well as a variety of classical solvers down here. So the most important thing here is that the D-Wave solver is a software interface with the D-Wave hardware. So there's actually never any direct contact with the D-Wave hardware. It's all taken care of in this solver up here. You have control over different types of embeddings, but beyond that, all the embedding is taken care of for you. So here's the full stack. Currently, it's under continuous development, and as you can see down here, only about 15% of the current work at 1QBit is in this stack. So the majority of the company is actually a part of the research branch of the company, while we have a small fraction that's developing this SDK. So the maybe 80% of the company is creating new algorithms to be put into this SDK by our software development team. Okay, so as I said, I'm going to go through 2 demos. They're live Python demos. I'm not sure if everyone knows how to program in Python, but it's pretty easy to go through, and I'll walk you through it. The first demo will be from the viewpoint of an analyst, developer, or student. This is someone, as I mentioned, that just wants to get a solution to an optimization problem without knowing anything about the underlying process. So I'll be solving the maximum k-plex problem. It's a relaxation of the clique problem, and it has applications in stock market analysis and community detection in social networks. Before I switch over, I'll just tell you about the second demo, so I don't have to switch back and forth from the live Python script. The second problem will be from the viewpoint of an optimization expert. This is someone that has been able to distill an optimization problem into a QUBO form and wants to test that this QUBO is actually working. So they'll access the functions from the binary polynomial layer to solve the k-coloring problem, which is also known as the map coloring problem, which has applications in airline scheduling and bandwidth allocation. Okay. So, as I said, the first demo is solving the k-plex problem from an analyst point of view. This first block, we're just importing a bunch of, first of all, can everyone see this in the back? It's okay. So these functions are just some graphical functions, graphical helper functions. The actual part that we're importing from the SDK is right here. So we're importing all the functions from the algorithms layer, all the functions from the binary polynomial layer, and all the functionality from the common solver interface layer. So I'll run this here. Next, I'm going to generate a sample graph that we're going to use for this problem. So if I generate here, this is what we're going to try to find the maximum k-clique. So the point of this problem is to find a dense subgraph of this entire graph. If we're taking the viewpoint of a financial analyst, we can consider each of these nodes to be an asset or a stock on a stock market. And if 2 stocks move together in some correlated way, we can connect an edge between the nodes. And the point is to find a dense subgraph of these nodes so that you have a highly correlated subset of assets. And this can be used for some hedging process or some portfolio optimization process. So the user will call this function poly-k-plex agent from the algorithms layer. We can define a D-Wave solver from the common solver interface layer. And then we can attach D-Wave to KP agent. And we can run KP agent over this graph G and print a solution. So it gives us 1, 2, 3, 4, and 9. And if we plot this again, we can see that we're actually given this minimum set, or this highly dense subgraph. So that's great. If you just want an optimization solution, you can just plug that in. You have your answer. But if you want to know more about what went on behind the scenes, you can actually dive into the binary polynomial layer. So if you want to know what the objective function was generated by that poly-k-plex agent, you can call this function getPolynomial for KP agent, and then print it here. So this is the actual objective function for this problem, and the minimum configuration of this will correspond to the solution of this graph. And we can call various things to find out what the degree, the term count, variable count. We have complete visibility into this layer. Of course, we have to transfer any polynomial into a binary polynomial in order to send it to D-Wave. So we have a function called hobo to QUBO agent that we can call. And we set it here and set QUBO to that function. We can print it here. So this will be the function that we actually send to the common solver interface layer in order to get a minimum configuration and a minimum energy. Also, we can get various properties of the QUBO, the density, the weights and biases associated with it. And then down here, we can actually, instead of solving this from the algorithms layer using poly-K-plex agent, we can send this QUBO directly to the common solver interface layer down here. So if we minimize that, we are given a set of minimal configurations corresponding to the minimum energy, or the minimization of that polynomial. So up to this point, we haven't cared anything about embedding or embedding strategies. We've been completely blind to the process. So just to show that we have control over what type of embedding we're using, I'm going to specify another embedding. So this is called specialized embedding strategy. This is from the common solver interface layer. And this is a heuristic embedding solver, and we can change various properties of it, so maximum improvement up to 50. I can then set the embedding strategy to the D-Wave solver here, and then solve the QUBO here. And as you see, I get another minimum set of configurations that corresponds to the solution we showed above with the same minimum energy. So this is a demo from the viewpoint of a developer or an analyst that just wants to access the off-the-shelf components in the algorithms layer. Next, I'll show a demo from the viewpoint of an optimization expert. So this is someone that has formulated QUBO on paper and wants to implement it using the SDK. So as I did before, I'm just going to import some graphical libraries so we can see what our practice problems are. We're going to import the binary polynomial layer functions and the common solver interface functions. Not going to import anything from the algorithms layer because we won't be using it. We'll actually be creating something that could be used in the algorithms layer. And then we'll define a practice problem here. So as I mentioned before, we're going to solve the K-coloring problem, which is the map coloring problem. It says, given a graph, and you want to assign a color to each node such that no two adjacent nodes share the same color. So we'll be solving this using QUBOs. Here I'm just defining a palette. This is where I'm going to call the colors from, and some helper functions to help define the QUBO. Here, as an optimization expert, I think that this is the right QUBO to solve the K-coloring problem. I'm not sure, but we'll find out. So I'm going to try to build this from scratch and then run it through the common solver interface layer and see what solution I get. So I'll show you how to do this. So from the binary polynomial layer, I'm going to call the function quadratic binary polynomial builder and initialize an empty QUBO here. So down here I have two loops. I'm going k from 1 to k and n from 1 to n. This will represent these two sums. So this block of code will actually be this first term here. So I'm going to add the term -1 as a coefficient times xnk, k times, and that will give us this section here. I'll add the constant term 1 from here, and I'll take the whole thing to the power of 2 here. I'll add this to the original QUBO and reset the builder and do this n times to get this sum here, and then we'll have the first term of the QUBO done. Likewise, down here I'll go over uv in the edge set and k from 1 to k here, and then I'll add a times xuk, xvk for the second term up here. So if I do this and show you the QUBO, this is what I'm assuming is the proper QUBO for this graph. There's actually some errors in the typesetting here, so I think there's missing some brackets in the LaTeX formulation. Okay, so I have a QUBO, I have a problem, I want to solve it, and I want to check to see if my solution is correct. So I'm going to send this QUBO to the common solver interface layer. I'm going to call a gray exhaustive solver, which is actually an exact solver, and see what the resulting configurations look like. So if I do that and plot the solution with colors, I see that, yes, it's solved the K-coloring problem, and I have a solution here. So this is the second demo from the viewpoint of an optimization expert. It shows you how you can actually construct QUBOs, send it to the common solver interface layer, solve it with D-Wave, solve it classically. We have access to all these functionalities. Okay, so I'm going to talk about the documentation. We've spent a lot of effort to create a very exhaustive documentation. I think it's around 350 pages now, which includes tutorials, example code, complete reference manual for all the operations and data structures in each of the layers. And I'll show you that in 1 second. It's written in C++, but there's a Python wrapper, which we just use for this. I can show you what the documentation looks like here. So as you see, it includes an overview, installation instructions, code examples, definitions for all the operations in the binary polynomial layer. The one thing I want to show you in this documentation is down here. One sec. So in the algorithms layer, so calling an algorithm from the algorithms layer is like calling a black box solver, and you have no real transparency into what's going on. So for each of the algorithms that we've provided, we actually have the exact QUBO formulation for this, which isn't typesetting right now. But for every algorithm, you can have confidence to use it and know that a proper QUBO has been sent to the common solver interface layer. The future releases for SDK, this is just very short term. We have a ton of other projects that are going to be placed in here. We have things like connected dominating set, job shop scheduling, restricted Boltzmann machines, which is what I've been working on personally. Added functionality in the binary polynomial layer. Lagrangian dual is a big project that's going to be a new solver in the common solver interface layer. The main point is that we've used D-Wave as an example to build an SDK because it's the only readily available hardware that we have access to. So we want to do this exact same thing for any type of hardware. So if there's new promising technologies that's coming out, we want to do this exact same procedure, this abstraction for those technologies. So we want to create a very collaborative SDK that everyone can use to provide access to their technology. So how to create an application using the SDK. This is sort of a flowchart to show how to use this in an appropriate way. You have to take your application, ask yourself, does the problem contain an optimization component? If no, then it's not suitable for the SDK. So don't do it. If yes, does the SDK have a built-in algorithm in the algorithms layer that you can use straight out of the box? If yes, call that algorithm and then receive your answer. If no, then we need to reduce the problem to a QUBO or an icing model or a higher order polynomial that then could be changed into a QUBO. So you do that, you get a polynomial. If you have a polynomial that is degree greater than 2, then call this hobo to QUBO agent that I talked about earlier. Send it to the common solver interface layer to one of either the quantum solver or the classical solvers. Map the solution of the QUBO back to the original problem and receive your answer. So it's a very straightforward methodology to use this. I think so. So for one of our test cases for using this methodology, we can talk about the molecular similarity problem that we had. So we want to take two molecules and we want to decide how similar these two molecules are. So the process is to transform the molecules into graphs. So I don't know if I have good enough hand resolution here. So atoms can become nodes and ring structures can become nodes, and the connections between rings and nodes and atoms become edges. We can send these two graphs to the SDK and call graph similarity, which is here, which is going to find a sparse subgraph of the conflict graph, these two graphs. We'll send it to the common solver interface layer. We'll get an answer of the QUBO and map it back to the original molecules. So we've done this. This is one of our big application projects, and I can show you the solutions here. So we have these very complicated molecules. I have two of them here. I'm not going to name them because it's a bunch of letters and numbers. So we have CC1 and CC4. This is running live right now, so we've solved this problem in real time, and we can see that the result gives us the actual answer to the similarity problem. And we have a score up here that is what we need in the end. Okay, so we built this SDK and we want people to use it, so why would you use the SDK? We want to bring optimization using 80-beta quantum computing, as well as other type of quantum computation to users who are not necessarily experts in this field. We want to introduce a paradigm or a programming pattern for people to create quantum-ready solutions, or solutions that classically can be solved but should be solved on quantum computers. We want to reduce development time. We don't want to have to create algorithms from scratch. We don't want to have to create QUBOs every time. We don't want to have to embed them onto quantum computers every time. So that reduces the development time to create new applications for quantum hardware. And we also want to create a very open collaboration with everyone that's creating quantum computers, so that we can share code, get together and create really cool algorithms. Most of all, we want to build a community. So we are actively seeking collaboration. We're interested in learning and experimenting with other hardware and simulators, and this conference has been a real eye-opener for me. I'm not really from the hardware side of things, so it's lots of really cool things going on. So we really want to collaborate with you guys. We're going to have a beta release later this year. We're planning on it. So if anyone's interested in trying out the SDK or trying out D-Wave using this SDK, we are looking for people to participate in this. So thank you very much. Appreciate it.
Okay, so this talk is open for questions.
So you've put together what looks like a cool SDK for the D-Wave machine,
Yes.
Which is based on QUBO as kind of its native language.
Yes.
But then you suggested that you wanted to define SDKs for other quantum computing machines,
Yeah.
and a lot of the rest of the hardware is focused on the circuit model of quantum computing, which kind of bears virtually no resemblance to this. What makes you think that the competency that you have for D-Wave will extend to other machines?
So we can totally separate from D-Wave at any time. So we have these 3 layers. We can separate the common solver interface layer into 2. So we have another solver for another type of computer. We can separate the binary polynomial layer into 2. So we have another way of constructing problems for other types of computers. And then leave the algorithms layer fully open. So we wouldn't have to have any relation to D-Wave whatsoever in the SDK.
Maybe just to add to that too, so the team is very diverse. We spent a lot of time, working on this because it's something we can experiment with. But the team that we pulled together aren't specialists in quantum annealing. And as we have an opportunity to really get our hands dirty with other technologies, we'd welcome the chance to collaborate and have partners who can bring the expertise for the hardware they're building.
Ashley.
So the companies and potential customers that you're talking to at the moment. So which problems are you finding that they are really wanting to solve? Like, which are the hard problems that they're finding too challenging to solve at the moment, and they're really interested in you guys to help them with?
So people that are coming to us now are people that are interested in the problems that can be solved by D-Wave right now, which include these NP hard problems, these classic optimization problems, but as well, they're interested in machine learning algorithms from Boltzmann sampling.
And what are the sort of application space that people are looking at? I mean, for what sort of industries are?
Well, we're targeting finance industries, we're targeting oil and gas, and pharmaceuticals. So the molecular similarity problem is a good example of that, of pharmaceutical and drug discovery.
Maybe I can ask a question, which is, so Dave Wecker gave a talk on the first day, and he was explaining how some of their approaches that they're taking and to solve certain problems are actually shedding light on improving the actual classical algorithms. So insights that they get from creating a quantum algorithm are helping them develop better classical algorithms, and I'm just wondering whether you guys are observing the same kind of behavior.
So there's new types of simulated annealing, simulated quantum annealing, or quantum Monte Carlo that are being developed using this as a model. So Matthias Schreier is developing some simulated quantum annealing that improves on that algorithm.
Right.
So,
Yeah.
Well, what we've been doing typically when we work with an organization is we've been providing what we're calling quantum-ready solutions. So we spend a lot of time providing an improved version of the classical algorithm of whatever they're running right now. And then we also provide a formulation that could run on a format that would work with a D-Wave machine currently. And if it's something that we get a better sense of other hardware platforms, we could look at it for other types of quantum hardware in the future. But it's a combined effort where you're providing both classical solutions today that often are quantum inspired, but sometimes aren't. And then as well as an actual formulation that runs in something like this. One of the projects that we put research out on not too long ago was optimal trading trajectories, and that was work that was done with Guggenheim, Morgan Stanley, Lawrence Berkeley National Labs representatives, and it looks at if you want to optimize a portfolio not over one period, but say over a year. So if you have 12 separate rebalancing stages, you're almost certain not to be multi-period optimal if you solved it every single period, and you incur quite a bit of trading costs and other things throughout the year if you do it every single period. So if you can look into the future and try and say, what's my estimate today that at the end of the year, what should that arc actually be such that I didn't trade to all the extremes, and it can reduce the trading costs or transaction costs, tax implications, moving the market, and things of that nature. So there are things like that that you can think about, and that's a research paper that we put out a few months ago if you're interested in looking at it.
Okay, any more questions? Steve?
So if someone wanted to try out your SDK who didn't have a D-Wave machine, how would you see that working? Are they running against a simulator, or is there a D-Wave machine out there somewhere that they can connect to? And if it is a simulator, what's the fidelity of the simulator versus the real hardware?
Do you want to actually comment on the access to D-Wave? Sorry, I'm deferring answers here.
Cool. There's a few components to that. One is you can choose a classical quadratic solver, so you could call any variety of classic solvers to see if you got the right answer. We have some different classical solvers built in. Two is we have our own simulator that we'll probably release as part of this, or alternatively hold on to it for a little while. And then the third is we have the ability to provide access through our SDK to the D-Wave system. And that's something that sort of can be looked at on a case-by-case basis.
Sorry, can I just follow up on that just quickly? And then, sorry, Pete. Access to the D-Wave machine, are you doing that through their own API, or have you got sort of more, even lower level access to the hardware?
So it's something where you have tokens and need to have an authenticated IP. So what could happen is if people are using the SDK, those problems could route back through us. Then they can go through our access and use our tokens in order to access the system. If you're like Steve and you have your own machine, then you could call your own machine instead. So it depends on who you know.
Yeah, Pete.
So we built a kind of microscopic equivalent to this in Bristol, giving people tokens to drive a chip around in our lab.
Right.
And you have this aspiration to be completely transparent whether you're running a simulator or a real device.
Right.
One of the things that I worried about when we were building that thing, it's a tiny 2-qubit thing, but I worried that handing tokens out to almost unvetted members of the public, can somebody attack my machine? Can they burn it? And if someone burns out a GPU, that's not too bad. But if somebody manages to actually physically damage a D-Wave chip, we're quite worried about that. So I wonder whether you've thought about that side of things and how you're dealing with it.
D-Wave does have control, or does know what's coming into the processor. So they have fail safes for that.
Right.
So I think it's pretty impossible to burn out a D-Wave chip. But that's a good question.
And from our perspective as well, Pete, we won't hand out tokens to anyone. So it'll come to us, and then we'll make the decision.
Yeah. 2-layer protection.
Okay, maybe time for one more question, if anyone. Any last question? Yep, Robin.
Okay, so this question is not as prejudicial as it sounds, and I just wanted to preface it that.
Oh.
If you're working with commercial customers, there is, to my understanding, generally assumption that you're running a thing on, they're running computer software, and computer software is relatively repeatable. It might have a random number generator in it, but at least that random number generator is well understood, and the Monte Carlo properties are well understood. Yes. The D-Wave machine is it's a chip in a dill fridge, and it doesn't always work. It may or may not find the minimum solution. I'm curious how you present that to your customers and what sort of liability issues there might be due to the fact that it might work or it might not.
Definitely. So at the moment, we're still solving small-scale problems using the D-Wave machine as we have limited qubits, and it's readily available for us to confirm that the answer we're getting is a correct answer using classical hardware. So in the future, as the hardware grows, that will become, I guess, more of a consideration. But if we're able to continuously just demonstrate at small scales we're getting the right answer, and if we can't get a better answer with classical hardware in the future as this problem gets larger and larger, I guess that'll be the way we look at it. But it'll be tough to know because as hardware does scale, and if you do get to the point where you can solve problems beyond the reach of a classical system, I'm not quite sure how you would check it.
Okay, maybe I'll ask one last follow-up question on that, which is from your perspective, how much better does the D-Wave architecture or machinery need to get for you guys to actually be solving real problems that the customers that you're talking to consider to be useful?
It's very different on a case-by-case basis. And if you can find problems that, as closely as possible, mirror the native architecture of the graph, you're going to get there a whole lot sooner. One of the things about going through the binary polynomials layer that Daniel was describing is it eats up a lot of qubits. You end up with a lot of overhead as you start to translate and abstract away from what that native QUBO looks like. So it would really depend on what problem you're actually solving. I don't think it's going to be a blanket thing where next year you switch over and every problem's solvable. Mm-hmm. You'll switch over and you might find one or two things where there's a sweet spot.
But even just the first problem, right? Are you able to give an indication of it? Is it a machine twice as complex, 100 times more complex than the current D-Wave system, or is it not the complexity? It's the reproducibility or the errors, or
that piece is also difficult to predict because as you move to new architectures and graphs, it's going to have more impact than adding more qubits at this point in time. Mm-hmm. So it's really, really difficult to tell on that point because I'm not sure what the next graph is going to look like. I've just heard rumblings that there's going to be one.
Fair enough. Excellent. Okay, so we can thank Daniel one last time.
Thanks, guys.
Thank you very much. Okay, so that's the end of this morning's session. We've got an hour break back here at 1 o'clock for the final session on quantum information and computation. Thank you, everybody.